Hey, welcome everyone. So today it is my pleasure to introduce Professor Samaya Nissanke from the University of Amsterdam. Samaya is an expert in gravitational wave astrophysics and especially multi-messenger observations. She obtained her PhD from the Institute of Astrophysics in Paris with a thesis on analytical modeling of gravitational waveforms. And after her postdocs, she moved permanently to the Netherlands, first to Radboud University, and then to the University of Amsterdam, where she's currently the spokesperson of the GRAPPA Institute. Samaya played a leading role in the multi-messenger observation of the neutron star coalescence in 2017, and has received multiple awards, especially the New Horizons in Physics Prize in 2020. So Samaya, please go ahead.
So thank you, Jimmy. You can all hear me, okay? Thank you, Jimmy, and thank you very much for the invitation. It's very special, actually, for me to be in Princeton and be giving this talk, actually, because it is Princeton where I actually first learned about gravitational waves and actually worked on gravitational waves as a summer undergraduate student visiting from the UK, almost 25 years ago, I'm embarrassed to say. And so it's really such a pleasure to be able to now talk about gravitational wave and multi-messenger astronomy here today. Okay, so the discovery of gravitational waves from a binary black hole merger in 2015, which was our most luminous event to date in the universe, has literally shaken and transformed modern astronomy. And it's this new spectrum, the gravitational wave spectrum, that is allowing us and is now accessible to us to probe the universe in new ways. And similar to the opening of the electromagnetic spectrum, we are able to actually probe new physical regimes as well as properties. However, it's this combination essentially of gravitational waves as well as electromagnetic radiation in the form of multi-messenger astronomy that is actually providing us with this immense source of astrophysical information. But however, this does come with many challenges that I'm hoping to discuss in my talk. Number one, actually interpreting and analyzing the gravitational wave signals. Number two, gathering real-time electromagnetic observations. And thirdly, actually interpreting these joint multi-messenger data sets. So without further ado, in the last 9 years, we have observed at least 90 compact objects with the LIGO and Virgo detectors over a period of 493 days during the first science run. So what you're seeing here is the mass schema. So in the vertical axis, this is the masses in solar masses. The horizontal axis doesn't have any significance. And the blue and the orange bubbles represent those black holes and neutron stars that we have observed in gravitational waves with the LIGO and Virgo detector. And the red and the yellow bubbles represent those black holes and neutron stars, respectively, that were previously inferred from electromagnetic observations. So there are a few things I'd like to point out to you. Number one, we're actually uncovering a diversity in the fundamental properties of these compact objects, with some broad distribution in the masses, with a few systems showing some asymmetry. Secondly, there are actually 20 other discoveries or mergers that have been discovered with other groups, aside from the LIGO Virgo KAGRA collaboration, including the one based at the IAS group. And in addition, last May, we began in 2023, the LIGO detectors began their fourth science run with Virgo joining in April this year. And over this period of 455 days, we now have about 170 significant candidates, including one bona fide event, GW 230529. The dates, these numbers represent the dates of the observations, which was our first neutron star and so-called mass gap event. The second thing I'd like to stress is that we still have open questions as to what is the nature of some of the progenitors as well as remnants of these systems with a few solar masses, whether they're neutron stars or black holes, as well as the existence of previously hypothesized mass gaps. As these have been the focus of my research over the last 18 years or so, I'm going to focus on this talk on neutron star, and neutron star black hole mergers, where at least one of the objects has matter in the form of a neutron star, and where we may expect electromagnetic emission due to the delayed matter outflows that are responsible for the radiation that we're observing from these systems. And specifically, I will be focusing on this game-changing first binary neutron star merger, GW 170817, which we observed both in gravitational waves as well as in every part of the electromagnetic spectrum, allowing us to pinpoint the source for the first time in the sky and allowing for multiple discoveries, the first Hubble constant constraint, the first association of a binary neutron star merger with a short GRB, the first kilonova discovery. So I'll discuss these through the talk. So the observations of this neutron star merger are traversing several diverse fields in astronomy and physics. And this is really thanks to the advances in gravitational wave detectors, time domain astronomy, as well as what's happening in data theory. And so I'll be talking about a couple of these areas in this talk, areas that I have myself as well as my group have been working on. So this is my talk outline, and I'll begin just by talking about the physics behind these observations and then these three recent advances, this discovery, as well as actually doing nuclear physics. If there's time, I would like to discuss some aspects of doing cosmology and end with perspectives. And the work that I'll be talking about has been done by previous and former members of my group in Amsterdam, as well as in large gravitational wave collaborations, as well as smaller electromagnetic time domain groups that I'm working in. Okay, so let's just remind ourselves, what is the driving motivation? So black holes themselves are the vacuum solutions of Einstein Fields equation. They represent the extremes of space-time curvature. And they have no surface. They just have an event horizon separating information from within the black hole with the outside universe. And they're the most fundamental and simple objects that we know of. Astrophysical black holes can be characterized by two numbers, their masses and their spins. Now, on the other hand, neutron stars, these are the most extreme dense objects that we know of in the universe, where matter is essentially compressed to several times the nuclear density in their core, and where fundamental and nuclear physics breaks down. Now, gravitational waves, these are an intrinsic prediction of general relativity. They are ripples in the fabric of space-time. They're sourced by these accelerating asymmetric matter sources. And importantly, our observable is this dimensionless gravitational wave strain, which importantly has this 1 over distance to the source dependence. And the lowest order, most dominant radiation is given by the so-called Newtonian quadrupole formula, where IIJ here is the mass quadrupole moment. They're coherent, they're weakly interacting, they allow us uniquely to probe the bulk dynamic properties of the matter, and they have two polarizations, H+ and H cross, that act as transverse tidal fields on the matter. And so this is exactly how the way these kilometer Michelson-Fabry laser interferometers are actually detecting these gravitational waves. They're measuring a combination of the two polarizations weighted by their antenna function, and essentially where they're measuring this fractional change in the arm length, which is proportional to the gravitational wave strain. And so we now have a global network of these detectors, the two LIGO detectors in the US, the Virgo detector, which I've been working with over the last 10 years, as well as the KAGRA detector in Japan. And one of really the motivations of building up this worldwide network is for multi-messenger astronomy, as I'll discuss. Now, during this frequency band, the most dominant sources that we're observing are these compact object mergers. And so let's look at GW 170817 and the signal. So shown here is the time frequency stamp of the signal, which you can see in yellow above the detector noise. This remains our loudest, our strongest event so far, a signal to noise ratio of 32, as well as our longest event. And what I'd really like to stress is this ever increasing frequency and amplitude, which we call the chirp. And we can understand how this frequency evolves by describing the system using a Newtonian description and essentially invoking energy balances, where the loss in orbital energy is equal to that Newtonian quadrupole formula that I showed you, the radiation. And within a couple of steps, we can get an expression for the frequency chirp, f dot, which is a function of this curly m, which we call the chirp mass. It's simply a combination of the two masses as well as f. I'd like to point out that the mass actually enters the dynamics as a time scale, g over c squared. So indeed, for cosmological distances where time is redshifted, the masses that we're measuring are also similarly redshifted. And so by measuring f and f dot as well as f max from this system, we knew that we were looking at a binary neutron star merger a few minutes after the event. Now, in order to actually extract information or more information from the signal, we rely on very accurate models of what the gravitational wave strain looks like. We call this the gravitational wave waveform. And broadly speaking, it comprises three phases, the so-called in-spiral, the merger, and the post-merger, or the ring down, where we can use a variety of analytical and numerical techniques to actually model this. And there are a few things I would like to stress. Number one, the frequency sensitivity of our detectors is more sensitive to a particular epoch in the waveform that depends on the masses. So in the case of tens of solar mass binary black hole mergers, we are typically observing the merger phase with tens of cycles lasting a fraction of a second. Now, in the case of those lower mass neutron star black hole masses, we are tracking thousands of cycles of the in-spiral, lasting a minute duration, so really allowing for very accurate or exquisite phase tracking potentially. The second thing I'd like to stress is this in spiral. We can actually model using the post-Newtonian approximation in general relativity, where 1pn here, v here is the characteristic orbital velocity, c is the speed of light. And what I'm showing you here is actually my first paper in my PhD, which was the 3.5 post-Newtonian equations of motion. What I really want to stress here is that these numerical coefficients that you can barely see, but are there, are actual direct predictions of general relativity. And indeed, general relativity predicts certain very unique signatures, such as the tail effect, saying something about the past history or the backscattering of the waves on the curvature, the absence of a horizon, as well as memory effects. And so we are able to do inconsistency tests of general relativity. The third thing I'd like to stress is that this in-spiral, as I mentioned, is driven by the chirp mass, and parameters such as the reduced mass appear at higher post-Newtonian order in the phase 1pn, and spin effects such as spin orbit at 1.5pn, spin-spin coupling at 2pn can cause a significant modulation and beating of the waveform. And this actually impacts how we can actually measure parameters such as the individual masses as well as the spins. Now, for objects with finite size, such as neutron stars, we are able to actually say something about the internal structure of the object by measuring what we call the tidal deformability that appears at 5 post-Newtonian. This becomes important as the orbital separation of our system becomes equivalent to the object's size. So in the case of neutron star binaries, we have an external tidal field that will induce a mass quadrupole and essentially accelerate the coalescence. And we characterize this with the characteristic tidal parameter, which is this ratio of the induced quadrupole over the tidal field, where K here is the dimensionless love number. This says something about the compressibility of the object. And R here is a new length scale we're introducing into the problem, the radius of the neutron star. So we're essentially dumping energy into these moving tidal bulges, which then accelerates the coalescence. And by measuring this tidal parameter, we can actually say something about the nature of ultra-dense cold matter by measuring or inferring the equation of state.
As you're describing it, this is not necessarily a general relativistic effect.
Yes, yeah, you're right. It just appears in the phase at 5 post-Newtonian, but in fact, actually, because of this becomes the numerical coefficient for this becomes important as you get closer. So actually, in the case of GW 170817, we tracked 4,300 cycles. It's only the last tens of cycles where tidal deformability information was possible to have some constraints. And indeed, this brings a very good point, is that we were not sensitive really to where we expect the tidal deformability to impact, as well as the post-merger remnant of the signature. Thank you. And so a big task to the community is really to incorporate more physics, include higher order corrections for the spins, for the tidal deformability, for eccentricity, etc., as well as to actually produce waveforms that also include beyond general relativity, as well as environmental effects into the waveform. So once we have these waveforms in hand, these coherent in spiral merger and Ringdown, we can actually then cross-correlate our detector output with template banks of 10 to the 5, 10 to the 6 waveforms, and not only do matched filtering to detect the waveform, but then to actually map out the posterior probability density function of the parameters that we can pull out from or retrieve from our waveform. So these comprise the redshifted masses, spins, tidal deformability, eccentricity, as well as, importantly, geometric properties such as the inclination angle, source position, and luminosity distance. And one thing I'd like to stress is these appear in the amplitude of our signal, where strong degeneracies exist. Indeed, each polarization, for instance, has a different dependence on the inclination angle. And once again, how we can actually measure these quantities really depends on the masses of the system and where the frequency of the detector is most sensitive to in the waveform. Now, typically, depending on the complexity of the models that we're dealing with, we are using random stochastic sampling methods such as Markov chain Monte Carlo or nested sampling. And this can take hours to days to weeks time scale to actually do this analysis for each event. And therein lies the challenge, where several groups, including my own in Amsterdam with PhD student Udita Bhardwaj, have actually developed simulation-based inference really to try to speed up this analysis, also very critical for multi-messenger astronomy. So what I'm showing here are the posteriors that we are obtaining for those neutron star, neutron star, neutron star black hole mergers that I showed you at the beginning. So these 2D PDFs, or probability density functions, for the larger mass as well as the smaller mass here. And you can see the chirp mass is tracking this particular line in phase space, where the error really determines the width of the bananas that you're seeing from the chirp mass measurement, and the reduced mass is determining the other direction in the error. And so these bananas really depend on the signal to noise ratio of the binaries, as well as what we are assuming in terms of the spin priors. But I'm showing this because really this plot is what is critical when we are trying to determine the actual nature of the compact object, whether it's a neutron star, whether it's a black hole, as well as in the future, tidal deformability will play a key role because the tidal deformability for black holes is 0. Okay, so I'm going to quickly just take a step back and tell you what we have learned so far. I'm really happy to discuss more of this later today, but I'm just going to quickly state. So we know now that compact objects merger as well as their merger rates. We can see that the neutron star, black hole merger rate still varies quite significantly. We know the rate of binary black hole mergers evolves as a function of redshift, that there's structure in the mass distribution with peaks at 10 and 30 solar masses, and that the component spins parallel to the orbital angular momentum appear to be small, but they're also measured very poorly. And there are some hints, if you look at the population, which are shown in blue and with extra events in red and green, show some hints of asymmetry and possible correlations. We can also put a limit, now an upper limit, on the fraction of the total energy density of the universe that is coming from gravitational wave populations. So I'll move on to GW 170817. And the story really begins, the multi-messenger story really begins in those first 2 seconds where the Fermi and integral satellites observed a low luminosity burst of gamma rays 1.7 seconds after the event. Now, for localization, we relied on the gravitational wave detectors. And what I'd like to stress is that gravitational wave interferometers on their own have very poor angular resolution. They have very broad quadrupolar patterns. So we really rely on triangulating the arrival time of our signals as well as some information on the quadrupolar pattern to actually localize the source. So in the case of GW 170817, we sent out alerts of the sky area of 30 square degrees with a distance of 40 plus or minus 10 megaparsecs at 5 hours after the event. And this allowed observers to actually cross-match this gravitational wave volume with known galaxy catalogs and allowed for the observation of this very bright blue flash at 17.8 magnitude that was seen in the galaxy NGC 4993 by the SWOPE telescope initially in Chile, followed by several other groups. And this really initiated this unprecedented global ground and space-based effort where over 100 instruments, 70 teams actually followed up the event. This is within the first month and a half, and this is where I spend most of my time over this on this event, was on this paper. And on the right here, what I'm showing here, I think really exemplifies the panchromatic beauty of this event. You're seeing the flux density as a function of time of the event over a period of 3 years. And these measurements are still ongoing in different wave bands. Now, what made it so impressive, having this compendium of observations, was that it agreed at 0th order with the prediction that there should be at least 2 types of matter outflows from these systems relating to the 2 electromagnetic counterparts that we saw. So the first is this kilonova, this rapid neutron capture nucleosynthesis powered transient that's thermally emitting in the UVOIR, lasting for a day, lasting for a week to 2 weeks period. And this resulted in the beautiful observations it's shown here by the VLT and ESO, indicating that this was one of the astrophysical sites of our process heavy elements. The second is the short gamma ray burst, where we were able to show that this binary neutron star merger is one of the progenitors of short gamma ray bursts and have insights into the relativistic jet. One of the many observations of this event that I'd like to highlight here is the VLBI observations that were taken at 2 epochs, 70 and 230 days after the event, that allowed us to actually constrain the shape and size of the jet, and allowed us to measure the proper motion of the centroid of the source, 2 to 2.7 milliarc seconds, allowing us to actually have an independent measure of the inclination angle of this jet, as well as the fact that it had some structure in the radial and angular distribution. And I will be coming back to that result as I talk about cosmology. And I'd just like to stress that both short gamma ray bursts and kilonova were first proposed by Princeton professor Bohdan Paczynski, actually here. So this really is one of the homes of electromagnetic counterparts and multi-messenger astronomy. So one other big task to the community is really being able to model the outflows and incorporate all the microphysics for these electromagnetic observations. And there remain many open questions despite the amount of information that we have. We don't know what's the origin of the blue kilonova, as well as what was the role of the jet-disk interaction, the central engine of the jet. So there are many exciting questions that require answering with future events. So now, since then, endeavor that my group, as well as other groups in the world, have undertaken is to actually jointly analyze and interpret these multi-messenger data sets. And this is non-trivial because of the large number of parameters. They're really yet to be really understood degeneracies, as well as the modeling challenges that lie ahead, especially for the electromagnetic counterpart, incorporating all the necessary microphysics. And in this light, my former PhD student Hert Rijmakers and master student Sella Melfor have been building and have built this end-to-end analysis observational tool, which allows one to actually ingest gravitational wave and electromagnetic radiation in order to actually do this joint analysis. And so the idea is really to map the binary properties to the light curves. And so, for instance, what the schema is showing is that if you take a specific binary with different masses, tidal deformability, spin measurements, one can actually map this out to the outflow properties, different types of the matter outflow coming either from the wind, disk wind, or dynamical ejector, and their velocities using semi-analytical formulae that have been calibrated to numerical simulations. And one thing that we have been very cautious in doing is really to make sure that we're incorporating all the uncertainties that can actually propagate. So we have a wide range in the outflow properties. And then for the second step, we use semi-analytical light curve models to actually map this to the light curves. And this is going to be hopefully out early next year in the Redback component. So one example of one of these semi-analytical formulae that I mentioned was looked at by my collaborators François Foucault and Tanya Hinderer in the case of neutron star black holes, and asking this question: is the neutron star actually tidally disrupted? Is there any matter outflows, or is it indeed swallowed whole by the black hole? And so what I'm showing you in this phase space diagram is the dimensionless black hole spin, the dimensionless tidal deformability for a mass ratio of 3, and the colors and the contours are indicating the matter outflow of the event. And so you can see that there's a really sweet spot where you expect there to be matter outflow for more puffy neutron stars, black holes with higher spin, as well as low mass ratios. And this information is actually sent out in the LIGO, Virgo, KAGRA alerts. And it also allows us to answer this question: well, what was the minimum neutron star radius needed for the tidal disruption of our observed few neutron star black hole mergers that we've seen? So what you're seeing here in red, this is our second neutron star black hole merger that was observed. In red are the gravitational wave posteriors. And you can see in this case, it's somewhat unsurprising that we did not actually see an electromagnetic counterpart. Only about 10 to the -6 solar masses would have been ejected. But indeed, if the black hole had a higher prograde spin, we may have seen more. Now, in the case of this event from last year, actually about 0.05 solar masses of ejector remained around the final object. And indeed, we should have seen an electromagnetic counterpart. Here, the challenge was that the sky area was about 20,000 square degrees because it was only seen by one detector. We can also use this tool to actually also do on-the-fly analytical, on-the-fly modeling of what the light curves should actually look like. So what I'm showing here are the different light curves one would expect using different model groups. And what I want to emphasize here are the wide uncertainties. And this is for the second binary neutron star merger, which we observed but did not see an electromagnetic counterpart once again because of the large sky localization. Now, most of this uncertainty, or one of the major uncertainties, is coming from the unknown amount of matter that is being ejected from the short-lived accretion disks that occurs for these neutron star, neutron star, neutron star black hole mergers. And so this can comprise two different parts, either a viscous thermally driven outflow or a magnetically driven outflow. And what we looked at in our paper was actually how future simulations as well as work, if we imagine actually constraining this much better from what you're seeing here in terms of the estimates that we use, these wide error bars, how this would actually propagate into our joint constraints of the fundamental source properties of this event. And so here you can see these were the then current state-of-the-art constraints for the viscous disk wind. But here we just had to estimate some 0 to 20% of the disk wind being released for the outflow. The other thing that we are looking into at the moment is actually understanding the different degeneracies and how they can be orthogonal to each other. So these are observations for a simulated GW 2304-529, this neutron star mass gap event, where we can see, I won't go in the interest of time through all of this, but we can see certain degeneracies that are coming from the electromagnetic side as well as from the gravitational wave side, particularly orthogonal to each other. Okay, so really trying to understand where does the improvement have to be in terms of simulations or in terms of how we do the observing strategy. And finally, neutron star mergers themselves are providing us this unique probe into the QCD phase space. So at high densities and low temperatures, where we may actually be able to map out the quark-hadron transition from hadronic to quark-gluon plasma. And in this case, what we were able to do was actually perform the first multi-messenger constraints for neutron stars in the mass radius plot using our two binary neutron star merger events plus two rotationally powered millisecond pulses that were observed with the NICER as well as with X-ray observations. So shown here are in the purple, these horseshoe seahorse contours are the 50 and 90% constraints on the mass radius plot, with the different colors showing different theoretical equations of state. And what other work has shown is that for signal to noise ratios of about 50, we need about 50 of these kind of measurements to actually start to really hone in on the equation of state. Now moving to cosmology. Sorry, I'm a bit parched. So Moving to cosmology, another beautiful example, I think, that exemplifies the power of multi-messenger was the standard siren measurement of the Hubble constant using this bright standard siren measurement method where we have the distance from our gravitational wave strain and the redshift from our host galaxy. So in blue here, what you're seeing is the PDF, the posterior PDF for that H0 measurement, and in green and orange here are the then constraints that were coming from the Planck, the CMB derived measurements, as well as those coming from the Schütz collaboration using Cepheids, the relative distance ladder using Cepheids and supernova 1A measurements. And as you are aware, there is this very intriguing 5 sigma tension between these two data sets. And the hope is that gravitational waves may come in and actually help to contribute in understanding where possible systematics could, or potentially new physics could be. Now, one of the big challenges with this observation is in the distance inclination angle degeneracy of the event. So this is the 2D PDF for that same event that you're seeing from gravitational waves alone. So this big banana. And you'll remember that I mentioned we had this VLBI constraint that allowed us to have an independent measurement of the inclination angle. So if we fold this in, you can see that this distance measure shrinks quite considerably, allowing for this improvement by a factor of 2 in this single measurement. And what I'd like to stress is that in order to reach the kind of 2% level, which is interesting to say something about the so-called Hubble tension, we need about 50 of these bright standard siren measurements. Or indeed, if we have VLBI measurements that are actually only plausible out to a nearby distance of about 80 megaparsecs, just using a root n argument, we showed that we need about 15 of these events, okay, to get to this competitive 2%. So now in the last 10 minutes, I'm going to end with my perspectives and mention a few of the challenges as where the field is going. So a question that I get asked a lot is, why have we not seen any further multi-messenger observations? And so what I'd like to just do is revisit this period of 2019 to 20, where we sent out a lot of these alerts, and there were many interesting neutron star the second binary neutron star merger, as well as this other potentially initially neutron star black hole merger. So for the alerts that we had during this period, about in 40 or 50, the median area was about 4,000 square degrees. And it was so large because it was dominated by these one detector events, whereas the median distance was 200 or 300 megaparsecs. And you can compare this to the distance of GW 170817, which was 40 megaparsecs with a sky error of 30 square degrees. So this really challenged the depth required, as well as the field of view, as well as actually the information being sent out being as accurate as possible. And indeed, the fact that we had such large sky areas at such distance is not a surprise, because these detections are volume limited, yes? So most of the detections that you're seeing are actually at threshold, yes? So much larger volumes than expected for golden binary merger events. And these were simulations that I ran not many decades ago, but almost, yes, 10, 15 years ago. The other challenge that we have faced is the need to actually characterize all the other astrophysical transients as well as variable stars that can appear in the gravitational wave volume. So in the case of the ZTF 13 gravitational wave events that were followed in 2019 to 2020, there were 2 million alerts. And after human vetting and actually announced to the community, there were about 100. 80, 70 of these were followed up by spectroscopy, and after detailed analysis as well as revised gravitational wave information, it ended up with 0 kilonova being detected. But this really stresses this challenge that we have had to face: the depth, the area, the characterization of time domain transients and variables, as well as actually having target of opportunity time, as well as on the gravitational wave side, being able to send out as accurate and precise information that we can about the source in a timely manner. And the opportunity that we face is that there is going to be an improvement in the gravitational wave localizations as the detectors increase in sensitivity, as well as the worldwide network expands. There'll be more golden binaries as well as new facilities. The second challenge is that we really have to expect a diversity of electromagnetic counterparts. GW 170817 was kind of unique in the sense that not only was it close by, but we observed it with a certain orientation where we could both see the gamma ray burst as well as the kilonova, comprising both a very bright as well as a possibly red component. And so we expect that there was a short-lived hypermassive neutron star. Now, depending on the total binary masses, the mass ratio, as well as the remnant, future electromagnetic counterparts may indeed look quite different, as well as the hope in the next years to actually make sure that we can actually go after any precursor information. Okay, so these are happening just before merger or during merger. The other challenge is to make sure that we have multi-wavelength observations to really piece together the physics driving the merger, the post-merger of these systems, and also to move or question ourselves about this paradigm that we'll always see a kilonova only with a short gamma ray burst. We have now at least 2 events where we're seeing the signatures of our process heavy elements also with long gamma ray bursts. Thank you. The other challenge, as we talk about the future, and I want you to bear in mind, is that different science cases require different data sets. So in the case of doing H0 or cosmological measurements, we are interested in getting the redshift and the energetics. But if we want to do detailed studies about the R process, we really need to have very, very detailed spectroscopy on the event. So this really also impacts the facilities that we need and in different wave bands for these different science cases. So we have, fortunately, these new facilities coming online, such as the Rubin Observatory, as well as the Square Kilometer Array, that are really allowing us to do this very systematic study of the time domain universe, as well as existing facilities such as this Wiki Transient facility, as well as BlackGem in the Netherlands has just come online. And we also have new facilities coming online, such as CTA, as well as the existing IceCube, and excitingly, these new UV missions that will be going up in the next few years to 5 years, the Ultrasat and UVEX, which are really one of their key science goals on the multi-messenger side is to really determine what was responsible for the bright UV counterpart that we saw with GW 170817. Now, on the gravitational wave side, we are moving in this era from individual objects to statistics. Shown here is the worldwide network as a function of time. This red arrow is showing that we are in the middle of this 4th science run. These are the predicted number of events that we expected. So the fact that we haven't seen so many alerts regarding these events is unsurprising. It is consistent with these merger rates on the lower side. And the numbers here that you're seeing are the sky averaged, inclination average distances for binary neutron stars. So these can be, of course, significantly bigger for these heavier binary black holes that we're seeing. Now, at the end of this decade, we hope to have LIGO India joining the network, and preparations are already underway for the upgrades in the 2030s, the LIGO A-sharp, as well as the Virgo Next project, where we hope to have a factor of 2 improvements, so 2 cubed in volume from the 5th science run. Okay, and excitingly, which I'd like to spend my last 5 minutes is talking about the next generation observatories, the Einstein Telescope and Cosmic Explorer. So what I'm showing here are the sensitivity curves for the various detectors. So here, this is the current sensitivity for 04, for the late 2030s, this A-sharp project. And then you'll see in the bottom, the sensitivity curves, projected sensitivity curves for the Einstein Telescope, as well as Cosmic Explorer, where you see this 10 times improvement in broadband sensitivity, as well as actually shifting the seismic wall to lower frequencies. Now, why is this desirable? Okay, it's really increasing the depth as well as the width of this frequency bucket that makes these next generation gravitational wave observatories so impressive. Number one, we can have extremely precise measurements for our high signal to noise ratio sources. Secondly, we can actually observe the epochs of, for instance, the post-merger for our binary neutron star black hole merger, their outcomes, as well as as well as more of the in-spiral for our heavier binary black hole mergers, so to track more of the in-spiral for parameter inference. Thirdly, to actually discover intermediate mass black hole mergers. And fourthly, just the sheer number and wealth. So the Einstein Telescope is a project being pursued in Europe. Its original plan was to be a single observatory that would be located more than 200 meters underground, and that would comprise 3 nested interferometers in this triangle configuration with 10-kilometer tunnels. And the aim is that the sensitivity is about 10 times better, so 10 cubed in terms of volume, and would be a facility lasting 50 years. Now, in the US, there's the Cosmic Explorer project, which is the partner project to the Einstein Telescope, where the aim, because there's much more land in the US, you can actually talk about building a 40-kilometer and 20-kilometer L-shaped detector with an increase of 10 times sensitivity. And so I would like to end by really stressing why these detectors are just so impressive. So what you're seeing here is the cosmic reach of the Cosmic Explorer, very similar for the Einstein Telescope. So here's the redshift as a function of the total binary mass for different signal to noise ratios. Okay, and shown, and so what these next generation detectors will allow us will be to observe almost all the binary neutron star mergers shown in these yellow dots, neutron star black hole in red, as well as white binary black hole mergers in the universe. This factor of 2 improvement in sensitivity will also allow the observations of new populations of black holes, such as population 3, as well as speculative primordial black holes. And what you're seeing overplotted here are the first binary black hole merger, as well as this GW 170817 in this phase space. So what I'd really like to stress is that we have to be prepared for these hundreds of thousands of binary neutron star mergers per year, as well as the 100,000 binary black hole mergers that we may actually be seeing this year. And the second thing is the sheer the reach of these detectors, yes? So we'll be able to actually probe the peak star formation, a redshift of 0.6, where the majority of fast radio bursts is happening, the highest GRBs at a redshift of 8, as well as the highest galaxy candidates at redshifts of 11 to 13. So really being able to go to very, very high redshifts. And we can lay this in comparison with the current detectors that we have today. And we can see that currently, as well as even the upgrades, will only allow us to actually probe a small fraction of these populations. Now, what I'd like to stress is that in the early 2030s, the GW1708-17 event that I mentioned would have a signal-to-noise ratio of 300 compared to the 30 today. And the individual mass errors would be on the 0.1 to few percent, and distance errors instead of tens of percent at several percent. Okay? If we look at Cosmic Explorer and Einstein Telescope, if we have the entire network operating, this would have had a signal-to-noise ratio of 1700. Okay, and the individual mass measurements of 10 to the -3 with distance errors on the percent level. I think I will finish that there. And so this prospect, where we're looking potentially at telescopes like the Einstein Telescope and Cosmic Explorer coming in the late 2030s, early 2040s, really requires a radical transformation in how we think of multi-messenger astronomy. This, the standard idea that we will follow up single sources will, of course, continue for the very, very loud nearby events where we can really do some exquisite measurements, multi-messenger observations, but the majority of events will, and simply the sheer number as well, we don't have the potential or the facilities to actually follow up all of the potential electromagnetic counterparts. So herein lies the challenge, where we will be using these systems really to also probe large-scale structure, the homogeneity and isotropy of the universe, as well as extragalactic astronomy. So the 2030s, what I'm showing in this donut plot in the radial distance is the look-back time. The different colors show the detection horizons for different detectors. The blue dots are the binary neutron stars that mergers that we expect to detect per day. The binary stellar mass black holes per week, and the binary supermassive black holes potentially with the LISA satellite per decade. Okay? And so it really is, you know, I've spoken or presented at the moment that we have potentially a couple of hundred of these events, but we're really looking in a relatively short time scale, if these projects are funded, to this huge transformation. So I will end here. I have really focused on only on the high part of the entire gravitational wave spectrum that spans decades of frequency space, and that is being probed by numerous methods such as pulsar timing array, as well as in the future we will have LISA, the LISA satellite, which has been adopted and is due for launch in 2034, 2035. And there will be many other sources, such as supermassive black hole binaries, as well as white dwarf binaries that will also have electromagnetic counterparts. So the future is both loud and bright, and I'll end with my conclusions here. Thank you.
Any questions?
It's going to be loud and bright on the gravitational wave side. I'm thinking about the optical follow-up challenge, because many of the optical counterparts that you'll be looking at will be at fairly high redshifts. And I wonder if you can say a few words about, well, first you have to find them, so that's the angular resolution, but then you want to do spectral follow-up and so on. Can you say a little bit more about what the challenge is on that front?
Yeah, actually, Michael. I was hoping to maybe talk about those aspects and have a discussion maybe in the Bacall lunch. So could I refer to, so yeah, if that's possible, it would be great to. I would also be very interested to have feedback as to how to move forward. Yeah.
So for studying the tidal effects, really like to have been able to go to a somewhat higher frequency, I guess. If an event like GW 1708-17 were to recur, given that it lasted 100 seconds, could one maybe have increased the laser power, during the event or something to get?
Yes, so GW 1708-17 happened in 02. So really, where the tidal deformability became, so basically the binary neutron star tracks part of the final stages will track part of the figure here in terms of the frequency space. And indeed, the post-merger is expected at a few kilohertz. Okay, so really, unfortunately, because it was 02, we did not see most of the tidal deformability information that even today we would have been able to actually pull out. But the hope is that, of course, and I will actually show a plot in the Bacall lunch for neutron star black holes, is actually that we will see the disruption or the merger actually with these next generation detectors. So be able to actually say something about the post-merger remnant as well. But yeah, unfortunately, just because the sensitivity curve was here. And so indeed, this is where we are increasing the laser power, as well as using squeezing, etc., to try to push this frequency bucket further down. I mean, I think one day it would be a fantastic to even think of having kind of adaptive interferometers. Yeah, but every time I talk to my experimental and engineer colleagues, they look a bit concerned when I share some of the hopes. But you know, there is a project actually in Australia called the NEMO detector, where actually the aim is just to focus to be a highly tuned kind of detector that will focus just on the high frequency kind of several hundred hertz kilohertz regime, just to focus on that question for neutron stars.
Okay. It's 12 o'clock, so I suggest there are more questions, we can move then to the Bacall lunch. So we can thank our speaker again.